and post it on YouTube within a day or so of the class. So if you need to see something again or you miss class, you got them there. Please do not use that as a reason to never come to class. That will become a problem and we'll have to chat about it. So one of the big parts, so math is a big part of my life, but the other big part of my life is Zen practice. And I like to bring part of that into my classes just because this world and this society is just kind of a mess, right? It's just a crazy mess. And you're every day you're here, you're rushing through your classes, you're asked to sit and absorb, and there's not a moment for yourself. So we're going to take each class just a minute to come into the classroom, to come into ourselves, and then to come into math. Maybe, hopefully a little more fully than we would. Thank you so much. Cool. So I won't do this every day, but I wanted to read you a little benediction for our class. This is going to be an adventure, and I am teaching this class differently than I have in the past. If you talk to somebody who took this with me last year at this time, you will be getting a very different course than they will. And the reason I changed it is because I talked to Dr. Gray, our resident, most senior physicist, and I asked, what is it that my students in DiffyQ should know? And then took that advice and modified this class so that we are, we're going to have you come out with some modern knowledge that's actually useful and applicable. So I'm going to ask you that if you're doing anything on a tablet or a laptop, you stop that for a moment, please, and come into the class. Thank you. So this is from Thich Nhat Hanh, who's a Zen priest in the United States. Brought Zen to the United States, and you've probably read stuff from him somewhere. Whenever there's someone trying to soothe someone else, the words of Thich Nhat Hanh have a good chance of showing up. So I just wanted to read you a couple of paragraphs here because I think it's germane to what we're doing here in this university and in this classroom, most certainly. As we sit down next to a stream, we can listen to its laughter and watch its sparkling waters, noticing the pebbles glistening and the fresh plants green nearby, and we may be overcome with happiness. We are one with the stream's freshness, purity, and clarity. But in an instant, we may find we've had enough, our heart is troubled, and we think of other things. We are no longer at one with the stream. It is of no use to sit in a peaceful forest if our mind is lost in the city. When we live with a child or a friend, their freshness and warmth can relax us. But if our heart is not with them, their precious presence is neglected and they no longer exist. We must be aware of them to appreciate their value, to allow them to be our happiness. If through carelessness and forgetfulness we become dissatisfied with them and begin asking too much of them or reprimanding them, we will lose them. Only after they are gone will we realize their preciousness and feel regret. Once they are gone, all our regrets are in vain. So we're here together. You've chosen to be here. You are not forced to be. I don't know, some of you might be forced to be here. I don't know what's going on. I hope to God you're not being forced to be here, because that's a terrible thing to be. But you're choosing to be here to learn, and to learn DiffyQ right now. So I ask that you just be present. And just remember how precious this opportunity is to be here. And sometimes, oh, fucking school, oh, it sucks, oh God, all this. There's so many other things that are so worse than being here. And this is a special treat and a blessing for us all to be able to learn some of the stuff we're gonna learn is ancient. Some of the stuff we're gonna learn is pretty recent. But to just be able to learn and play with these ideas, we are blessed. So let's just take, so I won't do that every time. It's like 10 minutes. But what we will do is take a minute to just come into this room. So if you wouldn't mind joining me, please. Close your eyes, you can keep your eyes open. Please pull away from the back of your chair. You don't have to do anything. I'm not asking you to do some religious practice here. You'll see. I'm just asking you to just really do absolutely nothing. Just settle in to this room and listen. There are sounds impinging on your eardrums. You don't have to do anything for those sounds to be. Find yourself moving into the future or what's already happened today, just listen again, gently, softly. Start class. Cool. So, file that out of the way. Let me get my little chart here. The way my class generally works is I will talk a little bit, present some ideas. We will work with those ideas together in class, and then I'll send you off to do your own work. And I have work for you already. Because this is a math class, we get busy right away. Homework 0. Homework 0 is due before class starts next Monday. So I guess you have less than up to 12:30. I suspect there might be people doing this at 11:29. Happens. All I want you to do is to log into WebWork. So if you go to our class page, let's go to World Class. Find the link to WebWork, which should be in the content area. Go to World Class, Content. You will find a section for WebWork. I've got everybody entered who at least was on the roster yesterday. If you added today or late last night, let me know. You probably aren't in the system, but you should be in the system. I've got instructions there for how you should log in, and your password is preset. I think it's your student ID. You probably want to change that. Nobody's hacking into WebWork so far. This is like the word, like, I think, you know, if you're a hacker and you're hacking into WebWork, you probably like need guidance as a hacker. Like, what the fuck are you doing? So what I would like you to do is to log into WebWork and start on any problem, not even correctly, just try. Go into the first problem, enter a 3. That's not the answer I'm going to gather, but enter a 3 so that I know you tried something, you know, or try the right answer. That's good too. So log into WebWork and start, and you just need to do this before Monday, and I will not extend this, and please, God, please don't make me beg you. Some people like to be begged. I don't like to be the beggar, but I end up doing it as part of my job. So that's homework 0. And then homework 1 is the thing you'll start on. So start on actually 2 things to start on. There is a warm-up of things you should know coming into this class that could potentially be shocking because they're calculus things. So basically the warm-up is a collection of integrals. And this is due, I think, next Tuesday. It's the deadline for this. I'll put this stuff into World Class for you, but it's in WebWork. It tells you the due date. Don't wait till the last minute. You're going to need to look stuff up, and you're going to want to ask about it in class on Monday for sure. I'm happy to review. Happy to review these techniques, but I have to know we need to talk about them. So this warm-up is just integration. That is the fundamental skill needed in this class. And then there's homework 1, which is not due next week. And if it is, I need to change that. That's kind of crazy. But what will happen is, this will actually be stuff we'll get to today. You will know how to start on this. It turns out homework 1 is a lot like the warm-up with an extra step involved. So it'll be more integration. You're going to get bombarded and immersed in integration for the next 2 weeks. And I think that's good. The syllabus, I don't even think I want to waste time on syllabus. That take that on. That was syllabus enough. But I'll tell you, the class is basically homework and 2 exams. So we'll have a midterm and a final, and I think those are each worth 20 points. And then everything else is homework. On this homework, if you've been with me before, you know how this works. You have infinite tries up until the deadline. So this is 60% of your grade. You have 100% of the control over your score. You just have to try. And I will, forewarning, even if you're good at integration, getting the right answers on these problems is sometimes a real challenge. There's like something that, oh, I missed this tiny constant somewhere, or I tweaked something. This gets hard and technical. So this homework here, you've got control over it, but if you wait till last minute, you're just going to be miserable. And then you're not going to have 100%. That's going to suck. The exams, on my exams are easy. Everything hard in my class is in this homework. The exams will be basic stuff, and I'll give you heads up if you've had class with me before. You know my exams are nice-ish, as nice as an exam can be, but I'll tell you what's going to be on there. It's not going to be the hardest things you have to do, it's this. Okie dokie. And my office hours are in the syllabus. They are right before this class on Mondays and Wednesdays. And then on Fridays at 2. Sometimes on Fridays those will be via Zoom. On Thursday I have Zoom office hours from 2 to 3. If you can't meet with me outside of those things, just let me know. And if you need help, we'll figure out a time to get together and talk about whatever's troubling you. 100%. So I think that's all the details. Does anybody have any questions on the process? No? Yes, yes, sir.
Where's homework 0 supposed to be?
It's not called homework 0. I think it's called warm up. Yeah. So this homework 0 is Voin, the homework 0 is just logging into WebWork and just doing anything. So it sounds like you just did it. Don't work on that during class though, all right? All right, thank you. And please bring your laptop when you can, especially Monday, because some days we'll just have work days where we're just literally working on the homework. The homework will be so involved that we'll need to take days to work together. And it'll actually make your life better outside of class. Which is a big part of what I'd like to do. So any other questions? Good, okay. All right, let's get going. Differential equations. When's the last, let's just go around the room really quick. What is the last math class you had and when?
Calc 3 last semester.
Calc 2
last semester.
You.
Probability and statistics over the summer semester.
Cool. When was the last calc you had?
Calc, that was probably my sophomore year, junior year.
You had it here?
Yeah.
Regis, awesome. Cool.
Stats class last semester.
And then before that, discrete math, probably.
Yes.
Because I know, because
Algebra,
yeah, okay. And we had Calc 2 together. Yeah, so
Cal 2 last semester.
Calc 2 last semester.
Linear algebra last semester.
Cal 3 last semester.
Calc 3.
Linear
Last semester.
Abstract algebra last semester.
Okay, all right, you're a math major.
We don't have this morning.
Okay, all right,
And Calc 3 and linear algebra last semester.
beautiful. How many math majors are in here? And minors? Cool, and physics, folks. Outstanding, beautiful. Everybody needs this. This is one of the fun math classes. If you like calc, I hope you like calc. For lots of reasons. You're probably in the wrong discipline if like calc was horrible for you. All these disciplines, like not liking calc would be scary. I would be worried about you because you're gonna do a lot of calc. But this is such a fun class. And part of what we're gonna do is very mathy and calculus-y. And part of what we're gonna do is very visual, and that's the part that I've changed in this class. We're gonna do two different kinds of analysis in here. We're gonna do a quantitative analysis, quantitative analysis, which is numbers and equations and solving equations and getting values and things. And then we're also going to do qualitative analysis, which is where we look at the way things flow and patterns and more holistic things than actual equations and numbers specifically. That'll come a little later. So let's get going. What is differential equations? And differential equations is the language of science. So when you say diff-EQ, differential equations, is the language of science. And I hope to convince you of that by the end of the hour. This is how scientists think. This is a tool for science. Math itself is a technology. Literally writing, you're all using technology, you're writing stuff down. Writing is a technology, math is a technology, this symbol is a technology. So the new technology we're going to learn involves symbols, putting them on a page that represent much bigger and deeper things than we could ever represent with just a sentence or words, or even just numbers. So what do I mean by that? Okay, so I take an object. I'm not going to drop tick not on. I kind of want to drop that, but I think something bad will happen. But I'll drop this. Take this notebook, hold it at, what, 5 feet? And I drop it. I'm a scientist. I want to understand that. I'm kind of curious, how fast was that thing going when it hit the ground?
Around 0.8 meters per second squared.
That is how fast it was accelerating.
Oh, right.
But how fast does it go when it hit the ground? Right, because it's sped up. Like right here, it's at 0 velocity.
Yeah.
Right? And as it drops, it accelerates at 9.8 meters per second every second. And so it depends on how long it took, but that change is happening continuously all the way down. So I want to model that. So I'm a scientist, and I go, all right, I need a variable. So I'm going to let h of t be a function that equals the height of an object at time t. But that 9.8 is going to be super helpful, Lou, so I'm super glad you mentioned it, because we're going to need it in a minute. What do I know? The only thing I know about this whole process is how high the book was when I started, and I know one other thing. I know the acceleration of gravity. I know that objects are pulled toward the Earth with an acceleration of 9.8 meters per second squared. Let's draw a little picture. So here's t, here's h of t, and let's call this is h sub 0. I would say call that h naught. I will call it that just because that's what I learned to call it that. That's my initial height. And I took the book and I hold it here and then I drop it and it's going to move downward. So this is Earth. Things are being pulled toward Earth by gravity, whatever that is. That's why I couldn't be a physicist. Most of the stuff in physics is like, oh, that's gravity. And you say, what's gravity? Oh, it's something else that I don't understand. Oh, it's something exerted by a mass. What's a mass? Oh, nobody knows. So I just prefer not to pretend like I have any understanding of these things, but I sure can work with them. So this thing is accelerating, but really the only thing I know, so only fact we have, and this was established probably by Newton. He probably used qubits per some weird ass unit of time before we had metric system. I don't know what Newton did. Maybe Newton had the metric system. What is the acceleration of gravity in feet per second? I'm almost glad you don't know. So it's 9.8 meters per second squared if we use metrics, kilograms, meters, seconds. What is it in feet per second?
3 something?
There is a 3 involved. 32 feet per second squared. Cool. Yeah. So this axis is the positive direction moving up. That's positive time moving that way. So that force there is acting in the negative direction of the way I've oriented things. If h is the position, what is this? What does that physics see? Velocity. This is the velocity. What is this? That is the acceleration. That is the velocity of the velocity. It's how fast the velocity is changing per second. So this is acceleration. Cool. I know this. Now I want to introduce a little notation that you're probably more or less familiar. Here's a jelly bean I lost this morning. Will not be eating that jelly bean, and nor will I be making that shot. So just a little bit of notation. Have you seen this notation before for derivatives? No? Okay, so this is like the prime, but with respect to t. So if I have a function, f of x, and I take its derivative, we often notate that like that. If I have a function with respect to time, it's very commonplace, especially in chemistry, I've heard, to denote that as a dot. So I'm just introducing some notation here. So this means the derivative of h with respect to t. Let's put that up here. Still a function of t. And so this is velocity of my object. But what we're working with is, the only thing we know is h double dot. Now that's the second derivative. That's this thing up here. So this is just notated double dot as opposed to double prime for the second derivative. So I use that, and that's a notation you'll see me use a lot. We'll do a lot of physics stuff in here. So the acceleration of this object is negative 9.8. I just wrote an equation. This is a differential equation. It's a differential equation because it involves the derivatives of a function. And I don't know what the function is, but look at what the difference is. Every equation you've ever had to solve up to this point in your life is a single variable. You're solving for X, you're solving for Y, you're solving for Z. What we solve for in this class are functions. Our solution is a function, picture a function. That's what we're looking for in a whole bunch of different things. So let's take this and let's actually see if we can come up with the solution. How do I move? So let's start here. This is the bit of review. So I've got this as my equation. How do I move to from the second derivative to the first derivative? What calc? Antiderivative, yeah, antiderivative. Because this way is the derivative. So what is the antiderivative of a constant? You've been helping. No pressure, but you gave me that great answer.
It's either 0 or negative 9.8x.
Yeah, it's definitely. The zero's this way, more derivatives. That's good, I like it. Hey man, out of all the possibilities in the universe, you came up with 2, and one of them's right. So I'm going to integrate this with respect to t. Integrate with respect to t. So not an x, but a t, doesn't matter. And so this is negative 9.8 t. And what's the thing you lose points for? Forgetting because you definitely did, didn't you? Probably. The math is just rolled off of Void. So sometimes he would occasionally drop a few quarters on the ground because he just had all these big bucks he was. So we have this constant here. And this constant, let's take a look at this. This is a function. So this is a function of t. If I replace t with 0, so what is this? Like, give me a sentence or just a couple of words, physics-wise, to describe what does this represent?
The height at 0 seconds. So the initial height.
It's not the height, but
velocity.
Initial velocity. So, right, so h dot is velocity. This is the initial velocity. Let's go back to my experiment really quick. What was my initial velocity? 0. Okay. I didn't throw it down. I didn't throw it up. I just let it fall. I didn't add anything to things. So this is my initial velocity. Oh, let's stay consistent. I'll call that h. No, I will not call it that. I'll call it v0. Sorry. All right, I'm going to integrate again. So we got this. Oh, we can rewrite this now. So this can be written as h dot of t equals negative 9.8 t plus the initial velocity. Now this isn't what the question was. The question was, well, I guess that actually kind of was part of the question, but what I want to understand is how this changes in time. I want to understand, I want to be able to tell someone in a tenth of a second it was this high above the ground, and in half a second it was this high above the ground. And it actually took this long to hit the ground. How long was that? We could figure that all out. So I want to move up to the original h. So I'm going to integrate again with respect to t. So I'm going to get, this is the derivative, so I get the original function. So think back, right? If this is the original function, I take a derivative, I get this. If I take the derivative of this, I get this. So I'm just moving backwards in the calculus chain. Can someone help me integrate this? Someone who hasn't helped me yet. What happens to the t when I integrate with respect to t? Take the antiderivative. T squared over 2. Beautiful. Power rule. Right? So let's go. So we got negative 9.8. And this t, I use the power rule. I bump up the exponent by 1. And I divide by the new exponent. So there's a half in front there. What happens to this constant with respect to t? Integrate that constant with respect to t. What do we get? Anybody?
Not T.
P naught t. It's just like we did before, right? This is a constant, so it moves to v naught t, and then what do I want to add? Constant, new constant. That new constant, notice that that new constant is going to be the height at time 0. Right, when t is 0, this is dead, this is dead. This should give me the initial height, which I drew up on the picture. Oh my gosh, we just did some shit Newton did. Newton was like completely loaded with money. Newton was rich. Newton decided, you know what I'm gonna do? I'm gonna go prove everything in the world, and locked himself in a tower, had servants bring him things, and rub his corns and whatever else Newton needed, powder his wig. You had to have a very powdered wig back in the day. So Newton did a lot, but he also had it pretty easy. So I'm going to simplify this now because I now know my solution. I now have a complete understanding of height. It is 9.8 divided by 2 is negative 4.9 t squared plus v naught t plus my initial height. Equation of motion. This is one of the equations of simple motion. For the book that I had, for my little book problem here, we could actually make it a little simpler because I didn't add initial velocity. So in the situation I started with, for our situation, h naught equaled 0, because I just dropped that book. So our height could be modeled as negative 4.9 t squared plus my initial height, because this is 0. Ooh, let's see if we can do something. How high is this? Dude, God, I don't know how to do meters. How many? Is it about 2 meters? You're 2, oh, come on up, come on up. Our 2 meter stick. Beautiful. So, okay. So we're right here. Let's just go 2 meters. It's so much more easier. Okay, you ready? So 2 meters. So let's see how long it takes to hit the ground. Anybody know? I don't know. Thank you. But we're going to find out. So, this is Voignot. That's his name. Initial height is 2 meters. Cool. So let's make our equation here. 2. I can now find how long it took exactly to hit the ground. What is the height when it hits the ground? 0. So to find the time of drop, set h of t equal to 0 and solve for t. So we've got, and I might need a calculator, friend. I'll see how far I can get. I don't think it's going to be very far. Solve for t, so move the 4.9 to the other 4.9 t squared here. Divide by 4.9. Definitely going to need a calculator. Could someone just simplify this side for me? It's more than a fifth. No, more than 0.4. 0.408. So t squared. And Voigne, would you do me the honors of a square root, please? I'm just guessing. No, that can't be right. That isn't right. Because that's 0.04.
0.64.
0.64. Thank you. Took that book exactly 0.64 seconds to hit the ground after we dropped it from Boyd's head. Not something you can figure out any other way. We built that shit from scratch. The power of it, the power of this, and a simple, not a simple, but an observation about the world, how the world worked. Let's do another one. This one involves radioactivity. I don't happen to have any of that on me. I hope none of you do. When I first got here, we had a physicist who was the oldest, the kind, wonderful gentleman, Norb. Norb. Yeah. That's not a name you hear much. No, so it sticks with you. He had unbelievable amounts of physics weird shit in this, like in the dungeon of the science building over here. Like this crazy shit. And Dr. Gray was taking it out and I was like, I'm a junk collector. I just get crap and keep it. I'm a hoarder of sorts. So all the crap's coming out and I'm like, hey, can I have that? Can I have that? So I still got some. You can stop by my office. I got some of the crap from the basement of the science building. Some of it's really, really neat. But one of the things they found down there was a radioactive rod. In the desk, the middle drawer of Norb's desk. So as Norb sat in his desk, there was a radioactive bar just sitting right here above lap level. You think Norb would have known about that?
Is he okay?
He is not, but he was like 90, so it's not because he didn't disintegrate in the middle or anything. Yeah, it wasn't, it could have been, but he did pretty good for a guy who sat under radioactive stuff for years, I'd say. So I don't have radioactive stuff on me, but let's imagine I did. Let's imagine I had a chunk, a cube of strontium. Let's say I had 100 grams of strontium. That's probably a lot. It's whatever, it's radioactive. Have anybody seen on TikTok just the people going and finding the radioactive plates in pawn shops? They glow. People ate off radioactive plates in the 50s. They're green. They kind of like this weird glow around them. It's crazy. So I have a piece of strontium. I just have to look these facts up. The half-life of strontium is 28.8 years. What does that mean? Somebody tell us. What does it mean?
Decays into its isotope after 28 years. Decays
Yeah.
into a different element.
Yeah, how much would I have after so I started with this?
Half of it.
Half of it, yeah. It's how long it takes for half the subject to, what did you say? Boy, that was so beautiful. What was it? Decay into its isotope?
Yeah.
Oh, that's nice. I just think it's gone. Apparently Norb did too, right? Didn't realize it's blasting his Nordness. So in 28.8 years, I've got 50 grams of it. And then in another 28.8 years, so 57.6 years later, and then how much do I have? 25. I have half that much. My cubes are decaying into their isotopes.
This would be decaying into a different element, not their isotopes.
Thank you.
Yeah.
That's it. So wait, say that again. Explain. Help me.
They just decay into a different element.
So what was the isotopes? You said something about
That
isotopes.
was just wrong. I don't think.
Oh, okay.
Yeah. Just
So you were wrong.
Yeah, I was wrong.
And I learned from you. Okay. All right.
Just,
Thanks. You still know 10 times more time. What is your name, Fred?
Evan.
Evan, thanks, Evan. I appreciate it. So let's look at the rate of change here. So here, we've got, let's let A of t equal the amount of strontium. There's probably some number that goes with that, like 238 or something weird, at time t. So here I have A at time 0 is 100. Here I have A at 28.8 is 50. And then here I have A at 20, easy, at 57.6 is 25. And that's grams. Just, so far, just noting things. I know the half-life and drawing pictures. There's really not much science going on. The science all happened before someone else did the science. So here, I want to talk about the change in A over the change in time. And delta is capital delta is the universal symbol for change. What is that equation, physicists? Ooh, yeah, I'm thinking, yeah, I guess S could stand for lots of things, so it probably is contextual. This is entropy. So the change in entropy in the universe is positive. The universe is decaying into disorder. This is why we have time right here. Yeah. Anyway, sorry, I'm just having fun. Which will happen often. Hopefully you'll feel the same at points. So the change here in this first window, the change in A with respect to time was negative 50, it's the drop, over 28.8. That's grams per year. If I go to this next window, the change in A with respect to time. Now I still have the same window of time, it's still 28.8 years, but the amount has changed by a different quantity. So the rate of change of the strontium cube is changing. And in fact, it's actually changing with respect to how much I started with. Right? So take a look. Right here, I don't know what that rate is. That's like negative 1 point. Somebody give me a calculator really quick, please. What is that approximately?
1.74.
Thank you. What is your name?
Katrina.
Hi, Katrina. Thank you. So negative 1.74 grams per year. And then right here, that's going to be half that number, right? So we can kind of wing it. We just have to take half that, so it's 0.8. Katrina, can you take 2?
0.87.
0.87. Thank you. Cool. Grams per year. But the key observation here is that the rate of change is dependent upon how much I start with, or how much I have at that moment. Like, these are big windows, but this same idea holds through. So let's just make the observation here. Observe. The rate of change in the amount of strontium depends. Ooh, let's use an old symbol. Boy, do people still use directly proportional? It's a cool symbol, right? It kind of almost looks like a zodiac thing. So that's like a little bowl on the side. Is I'll get rid of that. Is proportional to the amount at time t. Depends on how much I have. Now, this is on the big scale. These are average rates of change. What does this become, calculus, to put on your calculus mind, as delta t approaches 0? What calculus symbol does that turn into? Or the derivative. Yeah. So this turns into dA dt. Does this make sense, or should I talk about that? I'm happy to. Just let me know. Average rates of change become derivatives as the time interval approaches 0. It's instantaneous rate of change. So this is the instantaneous rate of change. And that's going to be proportional to the amount I have. So now I have a Diffie-Q. And that Diffie-Q is going to look like this. Here we go, we're doing science. dA dt is proportional, so I'll put a K here, that's a constant, the amount I have. K is a constant. I just observed nature, blackboard, whiteboard nature, and came up with an equation, just like a scientist would. I observed something about how things change, and I turned it into an equation. And we could even add this. At time 0, here's how much I started with, and I could say that was 100 right there. That's called an initial condition. This whole thing is called an initial value problem. We will solve many of these. You will be an expert at solving these by the time this class is over. You're going to be an expert at solving these in like 2 weeks. It's going to be great. So, I'm going to show you how to solve this in a bit, but I want to just tell you the solution right now, and then before the end of the hour, show you how I did it. Because I want you to understand what a solution is in a different way than we had over here. Now, this is crazy different than the first one I had. This is saying I can't just integrate to get the solution, because this over here is a function of t. So here, let's just make a little note here. Note, the dependent variable, good God, dependent variable, I'm cursing at my writing, dependent variable is A. The independent variable is T. If I have an equation like this, if I had dA dt equaled some function of t over here, some expression that was purely t stuff over here, I could use Calc 1. I could just go, oh, just integrate this side, so integrate with respect to t to get a, and over here, I could integrate, back on my constant, to get the solution like we did the very first problem. But that's because this is the independent variable purely over here. This is all t stuff. This is the independent variable, but up there, A is on the right. So the solution isn't this. I can't just take that thing and go, okay, integrate with respect to t. The left side becomes A, and then the right side is going to be K. What is this? I don't know. The problem is I'm trying to find A. So the solution to this problem, this is garbage. You might accidentally do it from time to time, but we will stop doing it. The solution to this is as follows. Here's the solution. And I'll show you how to find it. A of t is some constant c, different than the k, e to the kt. That's what the solution to this problem looks like. And let me show you why. And in understanding why, you're going to start to see that these things are different than the calc you've been doing. So first off, yeah, well, I won't get into it yet. Let's just keep going here. So show, here's like a problem. Show that A of t equals c e to the kt is a solution. I'm saying a solution because that's arbitrary. I want that to look like an equal. minus 2 dA dt equals Ka. So how do I prove something's a solution to a differential equation? I plug it in, do the derivatives that are needed, and see that it's true. So on this side, here, we're going to find dA dt. Could you actually do that for me? It's your turn. You'll usually be writing a lot more than this, but today's intro. Can you find the derivative of this with respect to t, kind of on your own, and then we'll share? As you start to crank the rusty wheel, you can hear it. It sounds like those caps coming off. Is that it? That's Of course, you actually need to know that formula. If you want to get a derivative sheet or something, print one out, bring it to class, it'll be handy if those things aren't fresh in your mind. Can anybody tell me that formula? So you take the derivative of the exponent times the original function left alone. There's a really special form of this that I would absolutely keep in my pocket and be ready to pull out at any instant. So a special form is d dt, and that t could be x or k or whatever. E to the kt is just ke to the kt. It's just nice. It just happens a lot. So it's a good, quick form to have. So when I take the derivative of this, what happens to the c? Lou, I saw you had it.
It's part of the original form, so you just leave it.
It's just a constant, so it comes out in front. So it's just c times the derivative of e to the kt, which is that. And if the right side was any more complicated, I might have to do something, but the right side just says take k times the function a. So this is the left-hand side, is this, that's LHS, left-hand side, and the right-hand side is just ka, which is k times that formula, ce to the kt. And you can see that these two things are the same. So that means this is the solution to this, a solution to this, no matter what c is, independent of c. C just rides along. If that's 3, that's a solution. If that's pi, that's a solution. If that's 0, that's a solution. All right. So now I could go through, let's finish this up, because if that's the solution, I still have this condition. So we know, and I'm going to show you how to find this in just a second. We know that a of t is ce to the kt for some c. We don't know what c is, but we're about to find out using this initial condition. Since a at 0 is 100 grams. Could you find C for me really quick, please? Maybe in your head you can do it. But find C. get stuck on this too long. Basically, I just plug in, take this formula, plug in 0. So A of 0, if I use the raw formula, is e to the 0. And e to the 0 is 1. So it's literally just c. This part becomes 1 when t equals 0. So c itself must equal 100. And so I rewrite my final solution. I now own that strontium. Almost. Why do I say almost? I don't know. What the fuck is K? Right? What's K? Any ideas on how to find K?
And we know that it takes 28.8 years to have.
That's it. So we're going to use the half-life to find K. That's the decay rate. So, still need K. Use the half-life is equal to 28.8. We've got some other data points, right? We know, i.e. we know that A at 28.8 was 50. 28.8 years later, I had half of my strontium. So I'm going to rewrite this. So this becomes, this is an arrow that I'm drawing, an implication arrow. This, with my newfound formula, is 100e to the k. I'm replacing the t with 28.8. And then that's equal to 50. And now let's see what else, other math. Today's a good math review day. Like almost every day is going to be a good math review day. Divide both sides by 100. Let me help you. 2. Yeah. What was that?
1.4.
Thank you, boy. Yes, correct, sir. 1/2. I'll be good. Yeah, 0.5 or 1/2. Thank you. I remember this. Appreciate you. So here's a fun and useful fact that you will probably need about a jillion times in the semester. That equation can be rewritten as the following equation. So that's equivalent to the exponent is the natural log of this thing over here. Those are equivalent statements. They mean the same thing. If you had this, you could rewrite it like this. So down here, I'm going to do that. I'm going to rewrite it and get k times 28.8 equals natural log of 1/2. Could somebody do that? I'm going to guess. I'm going to try to guess. That's my guess. That's a pretty shitty guess. We're not sending rockets to the moon on that guess. Anybody got a natural log of 1/2 for me?
707.
I'm just saying. Not bad. So negative 0.707. Divide both sides by 28. So k is approximately this number divided by 28.8. And could I please get that? I think you're multiplying by it. Yeah, so divide it by, please. And who knows? I mean,
0.024.
0.0. Yeah, that sounds good. Thank you. All right. Now we own that strontium. We can answer any question anyone would need to know about that strontium. So our final equation is A of t equals 100. That came from the initial condition. E to the negative 0.024 t. Cool. I can plot that out. I bet it looks like this. Here's time 0. Here's the amount of strontium. Time 0, I had 100. And this asymptotically we could know everything we need to know about that. I could ask you, how much strontium will we have? And remember, key thing to remember here is that T is in years. So you would just want to make sure that all your units were in years. How much strontium do I have in 2 years? And we could answer that question by just using that formula. Differential equations, amazing. But not fully amazing yet, because I'm just giving the answers, right? You still don't know how to solve them. So let's solve that differential equation. First off, let me stop. Any questions? I haven't asked that in a while. I'm sorry. I'm kind of excited. Might not even know if we have questions yet, right? Sometimes that happens. Okay, cool. So how to solve a very particular type of differential equation. How to solve what are called separable diffie-qs. For a while, the first part of this class is going to be different types of differential equations and how to solve them. There's a lot of kinds. And so you have to have this toolkit or a computer. Go to some AI and say, how do I solve this? Don't go to ChatGPT, I can guarantee you, it probably doesn't know how to do this. It would pretend it did really well though, but it probably doesn't. If you went to Wolfram Alpha, now there's a good pretender. So, how to solve separable diffie-qs? First off, what is a separable diffie-q? Well, if I have a derivative with respect to one variable, a derivative of one variable with respect to another. So literally, that triangle could be A, this could be T, but it could be X and Y or whatever. I got 2 variables in here. So and if this is equal to a product of 2 functions, each of which is purely in terms of one of those variables. So here I just have a product of triangle stuff and a product of square stuff. This is probably gonna seem weird. I'm gonna do a bunch of examples. You'll know what I mean, probably better by the examples than by my circles and squares. The key thing is use legitimate math moves to get this with the triangle stuff and get this D whatever with that stuff. So the plan is this: get all the square stuff with D square and all the triangle stuff with the D triangle. We want the D, this thing and this thing to always be on top of the fraction. Always on top of any fraction. That's literally the method right there, except that one last step is after I do that. So let's say I did that. And so it has to be legit math too. Sometimes you can get it, but you didn't use legit math. Right here, it's pretty easy. I would just divide both sides by whatever this expression is, and put it under there. So here I would have D triangle over G of triangle stuff. And on the right, I've got that F of whatever. I'm gonna multiply both sides by D squared. So in calc, they told you don't separate the derivative. In diffie-q, we do. We treat the derivative like you can pull this part apart from there. It's like an actual fraction for this method. And then, lastly, integrate. So over here, I'm going to integrate with respect to that variable, and over here I integrate with respect to that variable. So over here, it's going to be D triangle over G of triangle equals integral F theta, and then tack on a plus C somewhere. And do these, and you're done. And that's a solution. we might need to solve for one in terms of the other, but this is the heart of the method. Separate the variables with the appropriate differential, and then integrate. So let's come to this guy, which is so conveniently right there. I want to solve this. We didn't know how to do this moments ago. Here we go. I'm going to multiply across by the dt, and I'm going to divide by the a. So watch this. Here's the separation. So separate. Divide by a. Multiply by dt. Does that look cool? Yeah, yeah. Simple, right? It just multiply it apart. And now integrate. Integrate each side with the variable on that side. So over here, I'm going to have integral dA over a equals, and I'm going to pull that k out in front because it's a constant, integral dt. What's the left side? Yeah, natural log. And let's slap on some absolute values just for safety's sake. They teach you those in Calc 1. There's never a good reason for it, but there is now finally. We're going to throw them away in a second anyway, but natural log of absolute value of a. Now, how about that right side? Yeah, what's that become? KT. KT. Let's see. Looks a little like our original solution, but it's not, because now I want to solve for a. How do I solve for a? Say that again.
Would you exponentiate both sides, or would put it?
Yeah, exactly. Yeah, exactly. Or use that equivalence that I put up at the beginning. Yeah. So exponentiate both sides is a beautiful way to say it. Make e to this equals e to that. Or take this is the same thing as that. Kind of wrote it ass backwards. Exponentiate both sides. So this, I'm going to raise each side, make it the exponent on e. Now watch this. This left side, e to the natural log of a is just that a, the absolute values on. And this side over here becomes e to the kt plus c. That plus c came up with the exponent. But here's a fun trick we're going to do. You're going to just take those c's, and they're like little vortexes, and they're hungry for all the math you can cram into them as long as it's not a variable. So here's the trick one. First off, I'm going to write absolute value of a. I have to keep the absolute value on because that's still a positive quantity, equals e to the c times e to the kt. I use the property of exponents. They're kind of backwards. Right? If you were to multiply these two together, you would add the exponents. And now I'm just going to replace e to the c with c. This is just a constant. I can make it whatever I want by choosing c appropriately. So I'm going to absorb the c into the e, or just replace e to the c with c, and I get absolute value of a equals c e to the kt. So recall this was e to the c, but now I'm just calling it c. And now c could possibly be positive or negative, so I'm going to get rid of my absolute values. And that's what we came up with. That's our solution. I want to do one more. Got like 1 minute. I want to do one more. And it'll be on the video. You can check it out, if you so choose. So, solve. I would like you to do this one, please. So I have dy dx equals x over y. y with the dy, get the x with the dx, legit math only. This one just requires multiplying. So the y comes up, this is y dy. I'm gonna cross multiply. That makes sense. Yeah, that makes sense. Yeah. There you go. If this had been x times y, that would have been the right answer. Did I integrate? You did. You forgot your plus c, and that's how you got to that place, which is not quite. Could be right in one circumstance. Friends, since we are running out of time, I'll do this. Good news, you have a lot of problems to practice on. Homework 1 is just this. Bring your laptops on Monday. This is all you're doing. It'll be enough. I'm going to cross multiply, so it's y dy equals x dx. I'm going to integrate this side, 1/2 y squared. Tack the plus c on the side you want the independent variable. So like I want x to be my independent variable because I'm old and stuck in my ways. So this is going to become 1/2 x squared plus c. That's a solution. But if I want an explicit solution, if I want to solve for y and get a like y equals, I would have to do this. Multiply both sides by 2. Hey, suck it up, C. You don't want 2? I don't care. 2c is now c again. So much fun. Take the square root of each side, since I don't know if it's the positive or negative. That plus or minus would be decided depending on initial conditions if I had any. Right now that's not a function, right? That's a parabola that kind of looks like this. We want functions in general. Alrighty, friends. Woo. Thank you for being here. We're gonna have so much fun. Please bring your laptops. Please do homework 0 before the class starts on Monday. Now things get scary. Now things are gonna get scary. Are you mounted jumping?
Yeah.
Oh, we're gonna have a party group. Wow. Thank you, gentlemen. Nice meeting you. I think I should stop.
Stop what?
Just stop all sorts of things, but I think you. I should stop this.